Welcome to today's Trane Engineers Newsletter Live program. I'm Jeanne Harshaw, and today we'll discuss the 2022 version of ASHRAE Standard 15, the safety standard for refrigeration systems. We'll start with an introduction to the standard and review the refrigerant safety classifications. Then we'll explain the restrictions on refrigerant use, including special requirements for when using A2L refrigerants. Next, we'll go through some examples for calculating the allowable refrigerant charge using the new term EDVC. And we'll end with an overview of specific requirements for refrigerant piping and for machinery rooms. Standard 15 is under a continuous maintenance process, meaning that the committee can publish addenda at any time. The standard then gets republished every 3 years to incorporate any addenda that have been approved since the last cycle. The content in this program is based on the 2022 published version. Be sure to visit the ASHRAE website for the most current version, including any published addenda and errata. Finally, we know we can't address every aspect of the standard in this program, so I want to also mention that we have a recently revised Trane application manual that goes into more detail on the standard and how to design various types of refrigeration systems to comply with it. To cover the topic today, Steve Kujak, Trane's refrigerant technology leader, is joined by application engineers John Murphy and Chris Williams. Chris is currently a member of the Standard 15 committee, and Steve is a voting member and past chair of the ASHRAE Standard 34 committee. So John, can you start us off?
ASHRAE is one of several organizations that write standards for HVAC equipment and systems. These standards are developed following an ANSI process that requires collaboration and public review. Now, it's tedious and time-consuming, but the intended result is a well-researched consensus document. But ASHRAE doesn't have any authority to enforce its standards, so they're written in a way that can be incorporated into building codes. Typically, this is a two-step process. First, model code organizations such as the International Code Council look to industry standards and other materials for best practices to use as the basis for their model codes. In this case, I'm showing the International Mechanical Code. Then a state or other governing body adopts this model code into law, where it's then able to be enforced by building inspectors. Now, this is important to understand because several years can pass between publication of a standard and its incorporation into a local code. Changes in wording and sometimes intent can occur along the way. So the bottom line is, when applying Standard 15, be sure to also review the local code. Okay, so now let's get into the details of Standard 15, starting with the purpose and scope. As you read these sections, notice that the focus is on safety, even in the title of the standard itself. Therefore, if you ever have difficulty interpreting a particular section, just remember that the primary purpose is safety. The rest of Standard 15 details the design and installation requirements for all types of refrigeration systems, from a small window air conditioner up to a large water chiller. It applies not only to newly installed systems, but also to replacements or modifications if they change the function or capacity of the system. And it even applies to conversions to different types of refrigerants. Now, some of the requirements in the standard are general and apply to all system types. Others are specific to the type and use of the refrigeration system. The scope also clarifies that Standard 15 does not apply to residential systems that serve a single dwelling unit. That's in the purview of a new standard 15.2. Nor does it cover systems that use ammonia as the refrigerant. Again, it refers to other standards for that guidance. So I'll also note that while Standard 15 does include requirements for commercial refrigeration equipment, such as refrigerated display cases, we're not going to cover those systems in this program. We'll just focus on systems used for human comfort. Now, to determine which safety requirements must be met for a specific project to achieve compliance with Standard 15, the first step is to identify the safety group classification of the refrigerant. Then you determine the occupancy classification of the space served by the refrigeration system. And finally, you determine the system probability classification. Based on these three pieces of information, you can then identify the relevant safety requirements from the standard. For the first step, Standard 15 references a different companion standard. ASHRAE Standard 34 designates the safety group classification of various refrigerants, and it also provides relevant safety data that Standard 15 uses in its requirements. So Steve is going to spend a few minutes here to explain Standard 34. Steve?
Just a quick introduction of the safety classification system defined by Standard 34. Later we'll discuss how Standard 34 is used by Standard 15. Historically, refrigerants used in the HVAC systems are mostly classified in Group A1, for example R134A and R410A, and the ultra-low GWP refrigerant R1233ZD. That is, they had lower toxicity profile and do not propagate a flame in the presence of a strong ignition source. Commonly, Class 1 refrigerants are referred to as non-flammable. Other examples of commonly used refrigerants with alternate safety classifications are R514A, which is a B1 refrigerant, and R717 ammonia, which is a B2L refrigerant. Hydrocarbons like R290, which is propane, is classified as A3. Another commonly used A3 refrigerant is R600A, which is isobutane. These examples demonstrate that refrigerants other than A1 can be used safely. Many of the new lower GWP refrigerants are classified A2L, which have a lower toxicity profile with a lower flammability characteristics. Examples of Class 2L refrigerants are R32, R454B, R1234YF, and R1234ZE. Section 6 of Standard 15 references ASHRAE Standard 34 as the source for this refrigerant safety classification. Standard 34 has two purposes. First, it establishes a system for assigning reference numbers to refrigerants such as R410A. This helps avoid confusion caused by using brand names such as Freon or other complications of using the full chemical name or formula. Its second purpose is then to define the safety classifications and refrigerant concentration limits for all types of refrigerants. Like Standard 15, Standard 34 is under continuous maintenance. Safety data for new refrigerants is added by issuing addenda to the current version and then including those addenda in the following printings of the standard. First, I will cover toxicity classification system used in Standard 34. In terms of toxicity, the standard divides refrigerants into two classes based on the occupation exposure limit, or OEL, of the refrigerant. This is the concentration level to which nearly all workers can be exposed to for a normal 8-hour workday and a 40-hour work week without adverse effect. Refrigerants with an OEL equal to 400 parts per million or higher are designated Class A. Refrigerants with OELs less than 400 parts per million are Class B. Standard 15 uses the toxicity classification as one of the ways to define the type of refrigeration system that can be used and the required safety controls. Class A refrigerants are allowed directly in occupied spaces, while Class B refrigerants are placed in machinery rooms. Next, we will discuss the flammability classification system used by Standard 34. The standard classifies the flammability of refrigerants into four classes: essentially non-flammable Class 1 or no flame propagation refrigerants, and three classes that distinguish various degrees of flammability. Historically, most refrigerants used in HVAC applications have been Class 1 or no flame propagation refrigerants. In the end, there are non-flammables and three types of refrigerant flammability. There is significant discussion in the industry around the varying degrees of flammability and safety. But what you need to understand is flammables are flammable when a viable ignition source is present and the right concentration of refrigerant in the air. Working down from the top, starting with Class 3 refrigerants, hydrocarbons fall into this classification, like R290, which is propane, and R600A, which is isobutane, because they have lower flammability limits, LFLs, meaning you don't need much of the refrigerant for it to ignite. Class 3 refrigerants are easy to ignite and they propagate flames easily. I think most people have experience igniting hydrocarbons, propane or natural gas in their homes when cooking. Class 2 refrigerants have lesser flammability characteristics than Class 3 refrigerants. They have higher LFLs, but are still easy to ignite and propagate flames well. Class 2L refrigerants are characterized by having even higher LFLs, and they are more difficult to ignite. Typical static electricity dischargers will not ignite them, as well as many common electrical outlet dischargers or appliances like toasters. It is important to realize that while Class 2Ls are more difficult to ignite, these refrigerants are still flammable, and an ignition event can occur in uncontrolled situations. The search for new refrigerants which have desired low global warming environmental characters will result in the use of more flammable refrigerants, primarily Class 2L and Class 3. Many hydrocarbons are used today in small charge portable systems like refrigerators and freezers. To summarize, here are excerpts from the tables in Standard 34 listing the safety classification groups, OELs, refrigerant concentration limits or RCLs, and lower flammability limits or LFLs for several refrigerants. The standard also includes the OSHA toxicity code classification to reduce confusion. Not surprising, nearly all refrigerants in the standard are neither highly toxic or toxic. As an example, let's look at the highlighted data for 134A. You can see that 134A is classified as a group A1 refrigerant. It is an A, Class A because its OEL is greater than or equal to 400 parts per million. 134A is flammability Class 1, so it will not propagate a flame and thus has no lower flammability limit. In this case, 134A's refrigerant concentration limit is 13 pounds per 1,000 cubic feet. This RCL value is used to determine compliance with Standard 15, which we'll discuss and explain later in the program. Now let's look at Class A2L refrigerants like 454B, for example. This refrigerant is Class A because its OEL is greater than or equal to 400 parts per million, but it is a Class 2L flammable refrigerant, so the table includes a lower flammability limit, or LFL, which is 18.5 pounds per 1,000 cubic feet. The RCL for nearly all flammable refrigerants is typically controlled by the flammability limits, which is defined by dividing its LFL by a safety factor of 4. So Standard 34 serves as a companion to Standard 15 in that it defines the safety group classification and provides relevant safety data for each refrigerant for use by Standard 15. Now back to you, John.
Thanks, Steve. So I mentioned there are 3 steps for determining which safety requirements apply to a given refrigeration system. Steve just showed us the first step, which is identifying the safety group classification of the refrigerant. The second step is to determine the occupancy classification of the space served by the system. Now, Standard 15 defines these 6 occupancy classes to reflect the various uses of a building, as well as the ability of the people inside to respond in case of an emergency. For example, the institutional classification includes facilities where occupants may have difficulty evacuating, such as hospitals, nursing homes, or prisons. As you'd expect, the refrigerant safety rules are more restrictive for these types of buildings. But industrial facilities are at the other end of the spectrum. Because access to the building by the general public is typically prohibited, the safety rules tend to be less restrictive. The third step then is to determine the system probability classification. For this step, Standard 15 classifies systems according to the likelihood, or probability, that refrigerant leaked from the equipment could reach the occupants of the building. A high probability system is one in which the location of its components is such that leaked refrigerant from a failed connection, seal, or component has a high probability of entering an occupied space. Some common examples include a packaged DX rooftop unit, a DX split system, water source heat pump, a VRF system, or a PTAC. In contrast, a low probability system is one in which the location of its components is such that leaked refrigerant has a low probability of entering an occupied space. Now, probably the most common example is a packaged water chiller located either outdoors or in a machinery room. Now, with the safety group, occupancy and system probability classifications identified, let's look at how to determine which safety rules apply. Section 7 in Standard 15 includes several restrictions on refrigerant use, which depend on the classifications we just explained. And then Section 8 prescribes installation restrictions, which are specific to the type of refrigeration system being used. In general, these rules define how much refrigerant can be used in a given application, and then detail any restrictions or design requirements that apply. Then the standard includes a list of general requirements in Section 10. These apply to any type of refrigeration system. Now, most of these general requirements are self-explanatory, so we won't talk through them today. And there's also a Section 9, which includes requirements related to the design of the equipment itself. Now, much of this is in the purview of the manufacturer, so we're not going to dig into that section today either. So let's go ahead and look at the restrictions laid out in Section 7. First, the standard restricts the use of Group A3 or B3 flammable refrigerants to only a few exempt applications. Certain laboratories and industrial occupancies are exempt, as are small listed self-contained systems such as vending machines, refrigerators, or water coolers, as long as the refrigerant charge is very, very small. Also, equipment that is listed to certain UL standards may also be exempt, again, as long as the refrigerant charge is below the stated thresholds. And systems located in a machinery room or outdoors are also exempt. Next, the standard prohibits A2, A3, B1, B2L, B2, and B3 refrigerants from being used in a high probability system for human comfort. That leaves only A1 or A2L refrigerants to be used in this application. But again, industrial occupancies are exempt, as are unit systems with a refrigerant charge below the stated thresholds. Now note that in Standard 15, the term unit system and self-contained system are used interchangeably. They're defined as a complete factory assembled system that has no refrigerant containing parts that need to be joined together in the field, other than by a companion or a block valve. Now, as I mentioned, other than these exceptions, only A1 or A2L refrigerants are allowed for use in a high probability system. But for A2L refrigerants, due to their flammability characteristics, the standard prescribes special requirements in Section 7.6. Chris will talk through those later in this program. But even when the use of these flammable refrigerants is permitted, the standard places a maximum limit on the total quantity. For all occupancy categories, the total amount of A2, A3, B2, and B3 refrigerants used in a building cannot exceed 1,100 pounds. And for an institutional occupancy, this amount is cut in half. Beyond those overriding restrictions, if all or part of a refrigeration system is housed indoors, then Section 7.3 defines the maximum refrigerant charge permitted, using a compliance path depicted by a flow chart published in the standard. Now, we've recreated portions of this flow chart to help explain this compliance path. It starts out by addressing what I think of as the special cases. First, if the refrigeration equipment is listed and contains less than 6.6 pounds of any refrigerant, then as long as it is not located in a public corridor or lobby, the system charge is in compliance, provided it's installed in accordance with the listing and manufacturer's instructions. Or if the equipment is listed, self-contained, and located in a commercial occupancy, but not in a public corridor or lobby, then as long as it contains less than 22 pounds of refrigerant, the system charge is in compliance. So what if the system is located in a public corridor or lobby? In this case, it must be a unit system, and the maximum charge depends on the flammability class of the refrigerant. For Class 1, the non-flammables, we're to determine the effective dispersal volume charge, or EDVC, based on the volume of the occupied space served by the system. For any other flammability class, the EDVC must be the lesser of the values determined based on the volume of the occupied or non-occupied space, or by an equation provided that's based on the LFL of the refrigerant. In either case, the system's refrigerant charge must be no greater than the EDVC in order to comply. Now moving on in the flowchart, the next question is, are all the refrigerant-containing components of a low probability system located in either a machinery room or outdoors? If so, the system must comply with the requirements in sections 7.4 and 8.12. Now the term machinery room has a special meaning in Standard 15. It's a designated space that complies with the specific requirements listed in the standard. I'll discuss machinery rooms a little later in this program. So next, if the refrigeration system is listed and used in a laboratory with more than 100 square feet of floor area per person, then the system charge is in compliance, again provided it's installed in accordance with the listing. And then for the final special case, if the refrigeration system is located in an industrial occupancy or in a refrigerated room, the system charge will be in compliance as long as it meets all the requirements listed in section 7.3.3. Okay, as I said, those are what I think of as the special cases or special applications. If none of the previous characteristics apply, then for all other systems, the releasable refrigerant charge must be no greater than the effective dispersal volume charge. This EDVC again depends on the flammability class of the refrigerant. For Class 1, we're to determine the EDVC based on the volume of the occupied space. But for any other flammability class, it must be based on the occupied or non-occupied space. Now we'll look at the EDVC calculations in a few minutes, and then Chris will go through several examples later in the program. Next term, the releasable refrigerant charge depends on whether or not the system uses release mitigation controls, which limit the release of refrigerant by automatically isolating leaking pipe or equipment. In either case, the releasable charge must be no greater than the EDVC in order for the system to be in compliance. Now let me bring in Chris Williams here for a second for some help. Chris, what if the releasable refrigerant charge is greater than this EDVC limit?
Well, John, that would mean the charge is non-compliant, and you might consider one or more mitigations. The system could be equipped with release mitigation controls, which may result in a smaller releasable charge. Or you could increase the effective dispersal volume by connecting the non-compliant space to other spaces via natural ventilation openings. Or the system could be modified with an air distribution system. This would increase the effective dispersal volume by connecting the non-compliant space to other spaces via the air distribution ductwork. Last, a mechanical ventilation system could remove excess leaked refrigerant from the non-compliant space. By using the mechanical ventilation to remove the refrigerant, this refrigerant is no longer included when determining compliance with the EDVC limit.
We'll demonstrate these modifications when Chris goes through some examples later. But right now, let's look closer at this new term, effective dispersal volume charge. This is the maximum charge permitted for an effective dispersal volume. It's calculated by multiplying the refrigerant concentration limit by the effective dispersal volume, and then by an adjustment factor for the occupancy classification. Now, similar to previous versions of Standard 15, this concept is based on a maximum allowable concentration of refrigerant, the RCL, that could result from a complete discharge into the volume of a space. If the releasable charge is less than the EDVC, then the concentration in that space should not exceed the RCL. The effective dispersal volume then is the volume of a space or connected spaces into which refrigerant is expected to disperse in the event of a leak. Now, as we mentioned earlier, which volumes to consider depends on the flammability class of the refrigerant. For Class 1, we only need to consider the occupied spaces served by the system. But for flammables, we need to consider both occupied and non-occupied spaces. Note that if a space contains only continuous refrigerant piping or joints and connections that have been attested in accordance with Standard 15, it's exempt and doesn't need to be included in these dispersal volume calculations. Chris will explain more about this later. Now, in calculating this effective dispersal volume, it's helpful to think of rooms in terms of non-connected spaces and connected spaces. A non-connected space is an enclosed space that contains part of a refrigeration system but is not connected to other spaces. Refrigerant released into a non-connected space essentially stays in that space and does not disperse into other parts of the building. Some examples might include a hotel guest room that includes a P-tack along the exterior wall, or a private office with a high sidewall terminal unit that's part of a VRF system. In this case, the effective dispersal volume is the volume of this individual non-connected space. On the other hand, connected spaces are two or more spaces that are connected by either permanent natural ventilation openings, a ducted air distribution system, or mechanical ventilation system ductwork. Refrigerant released into a connected space or into the air distribution system can disperse into all the connected spaces as well as into the distribution ductwork itself. So for connected spaces, the effective dispersal volume is greater than just one individual room. Now, in previous versions of Standard 15, it was left up to the design engineer to determine what constituted a suitable permanent opening for connected spaces. The 2022 version, however, now includes prescriptive requirements for these openings. First, spaces connected by these openings must be on the same floor of a building. Then equations are provided to determine the required minimum size of these permanent openings. The lower edge of an opening between connected spaces must be no higher than 12 inches above the finished floor, and any area of the opening that's higher than 12 inches cannot be considered for meeting the minimum size requirement. So next, for spaces that are connected via a ducted air distribution system, you can sum the volumes of all spaces that are served by common supply and return ductwork. Unless a space can be totally closed off from the source of the refrigerant leak by something other than a smoke or fire damper. Now, the standard specifically addresses VAV boxes and clarifies you can include the volume of the space it serves as long as the box does not close below 10% of its design airflow. You can also include the volume of the supply and the return ductwork itself, as well as the volume of the plenum if it's part of the supply or return air system. One common example is a DX rooftop unit, where the evaporator coil is located in the airstream that supplies air to several occupied spaces in the building. So that's a brief explanation of the allowable effective dispersal volume charge. Now, how about that other new term, releasable refrigerant charge? Section 7.3 defines how to determine this. For a system with a single refrigeration circuit, it's the entire charge of that system. Or if a system has multiple circuits, it's the charge in each independent circuit.
John, that is an important point. Standard 15 only assumes the first point of failure. This means you don't need to sum all the changes for all the systems. Rather, you're concerned with the amount of refrigerant that would completely discharge from an independent circuit. If a space is affected by components of more than one system, or a system with more than one circuit, the calculations are only per circuit.
Thanks, that's a good clarification. Now, another change to Standard 15 is that it now allows you to lower this releasable charge in the system if it's equipped with release mitigation controls that automatically isolate the leaking pipe or equipment. An example might be shutoff valves that close off the flow of refrigerant if a leak is ever detected. Now, this section goes on to prescribe how to calculate the amount of refrigerant that is expected to leak prior to these controls being activated. This then becomes the new releasable refrigerant charge for comparing against the EDVC. Now, it's important to note that Standard 15 does not permit reducing the releasable charge using these controls for an occupancy classified as institutional. And in order to take credit for these controls when calculating the releasable charge, they must comply with all the requirements listed in the standard. Now, I don't have time to talk through each of those requirements today, but I'll highlight a few. First, the release mitigation controls must be components of equipment that is listed, not an add-on in the field. Next, these controls can only be used to reduce the releasable charge in a system where each indoor unit has a cooling capacity of 5 tons or less. And the controls need to be tested before the system can be placed into operation. Now, I know that's a lot of content on the standard itself. Shortly, Chris will walk through several examples to show how these requirements and calculations apply to some common system installations. In addition, the application manual listed in the bibliography includes more details on these requirements and some other examples.
Thanks, John. So far we've talked about refrigerant safety group, occupancy, and system probability classifications, and how those are used to determine Standard 15's restrictions on refrigerant use. Next, we'll overview the special requirements that relate to the use of A2L refrigerants in high probability systems. Chris?
As John mentioned earlier, Standard 15 prohibits most classifications of refrigerants from being used in high probability systems for human comfort. That limits the designer to either an A1 or an A2L refrigerant. As A2L refrigerants are low flammable, Section 7.6 prescribes special requirements. The first requirement is that the equipment must be listed in accordance with one of these two safety standards. While UL 484 is discussed in the standard, for the purpose of this conversation, we're going to focus on UL 60335-2-40. Manufacturers are likely to follow the requirements of this UL standard strictly to ensure that their products are listed. However, depending on the application, it's possible that a specific requirement of Standard 15 could be more stringent than what's required by UL. Next, when a Group A2L refrigerant is used in the occupied space, the calculation of the maximum allowable charge is different, is included in Section 7.6.1. This limit depends on whether or not the system has air circulation to disperse the refrigerant in the event of a leak. Let's first look at systems with air circulation. Standard 15 defines air circulation as mechanically inducing airflow within a space or spaces connected by air ducts. This air circulation can either be continuous or it can be initiated by a refrigerant detector. As 24/7 fan operation may conflict with ASHRAE 90.1, the most reasonable option will be to use a refrigerant detector to activate circulation. Regardless of whether the fan is continuous or not, in the event of a leak, the minimum circulation airflow is defined by the product listing. With air circulation, the EDVC is calculated by multiplying the effective dispersive volume by the refrigerant's LFL. We're going to include a factor of safety. This shows up in the formula as 0.5. Finally, we're going to include an adjustment factor for the occupancy classification. If the occupancy is institutional, we need to reduce it by half. Next, let's look at systems without air circulation. In this case, the EDVC is calculated by looking up the charge limit M from a table in the standard. The designer then multiplies that value by a conversion factor based on the refrigerant used. And finally, by the occupancy adjustment factor. Here's an excerpt from Table 7-1 in the standard. The refrigerant charge limit M is based on the floor area and the height of the refrigerant where it is released into the space. The floor area is calculated as in Section 7.2, and the height is the lowest point of any opening in the supply duct, the return duct, or in the equipment itself. This is the lowest height leaked refrigerant can enter the space. The larger the floor area, the higher the refrigerant charge limit. And as the release gets higher, the charge limit also increases. This is due to the refrigerant dispersing wider as it drops to the floor. The next part of Section 7.6 requires a refrigerant detection system in the following cases. Any ducted system that has a releasable refrigerant charge greater than 4 pounds, and has a duct opening lower than 5.9 feet above the floor requires a refrigerant detector. Also, any ducted system in which connected spaces are served by the same supply air duct and are used to calculate the effective dispersal volume also requires a detector. And last, any system installed in an institutional occupancy requires a detector. When required, this refrigerant detection system must be integral and listed with the equipment. This detection system must meet all the requirements listed in the standard, and it obviously must be capable of detecting the specified refrigerant. When exposed to a refrigerant concentration of 25% of the LFL or greater, the detector must generate an output signal within 30 seconds. This signal initiates the safety mitigations. These devices are required to be factory set and cannot be field adjusted or calibrated. This prevents unauthorized adjustments. The detector must also include self-diagnostics, and if it fails a test, the equipment must energize its air circulation fan. Finally, the device must be modular and accessible for replacement.
Chris, you mentioned that this equipment must be listed with the UL product safety standard. And I know that standard also includes requirements for refrigerant detection. Are they the same?
Actually, yes. Standard 15 specifically clarifies in the appendix that a device meeting the UL product listing meets the requirements for a refrigerant detection system. Once the refrigerant detection system generates the output signal, the following mitigations must occur within 15 seconds. The system will simultaneously energize the air circulation fan in the equipment, while opening any zone dampers to their maximum airflow set points. Any electric resistance heaters or other potential heat sources must be deactivated. If installed, the system will activate release mitigation controls like safety shutoff valves to minimize the releasable charge. If it is required, the system will also activate mechanical ventilation. These actions must continue for at least 5 minutes after the refrigerant concentration has dropped below the mandated threshold. Next, if a ducted system experiences a refrigerant leak, it's critical to prevent ignition in the ductwork. Therefore, any open flame producing devices and unclassified electrical devices cannot be installed in the ductwork that serves the space. However, hot surfaces that exceed 1290 degrees Fahrenheit are permitted. The standard simply requires a minimum face velocity of 200 feet per minute across the hot surface, and it must be interlocked with a proof of airflow device. This device ensures airflow before the hot surface is energized. If the refrigerant charge in an independent circuit exceeds the EDVC, the mechanical ventilation may be an option to remove excess refrigerant from the space. Note that the term mechanical ventilation as used in Standard 15 is different from how the term is used in Standard 62.1. In Standard 15, in the event of a leak, ventilation simply refers to the minimum airflow required to evacuate the refrigerant to a safe location. This does require the use of a separate exhaust fan, and the safe location must not exceed the EDVC. The mechanical ventilation airflow can be determined using lookup tables in the standard or by this equation. As clarified in the standard, M sub S minus EDVC is the portion of the system charge that is removed by mechanical ventilation, so it is not included when determining compliance with the EDVC. Designers will most likely use this approach when they have a piece of A2L equipment lacking a circulation fan. However, it's not limited to those applications. I'll walk through an example in a little bit. This ventilation system must then meet all the requirements listed in the standard. This ventilation can either operate continuously or be activated by a refrigerant detector. Makeup air must be provided with openings positioned to allow this makeup air to mix with leaked refrigerant. Intakes for the exhaust air must be located such that the bottom of the intake air is no higher than 12 inches above the lowest elevation in the space where leaked refrigerant is expected to accumulate. Discharge of this exhausted air must be located to prevent recirculation back into the space. And no open flames or hot surfaces can be installed in the space where the equipment is located. In addition, the standard requires this ventilation system to be verified by a monthly self-test to confirm operation.
As John mentioned earlier, we know it's difficult to listen to us talk through the requirements of a standard like this. So next, Chris is going to go through several examples for some common system types.
As John explained, when there is a complete discharge of refrigerant into a space, the refrigerant charge must not exceed the effective dispersal volume charge. So let's step through a few examples of calculating this EDVC. First, we'll start with a small package rooftop unit serving a classroom. Then we'll look at a VRF system serving a commercial occupancy. Next, we'll look at a package VAV system in an office building. And finally, we'll review 2 indoor water chiller installations. Before we start these examples, it's not going to be possible to show all the math. If you'd like to see the gory details, please review Trane Standard 15 2022 Application Manual. This document will not only show all the math, but it will go into greater detail and explain where the givens came from. In this first example, a 5-ton package rooftop unit serves a classroom in a K-12 school. This rooftop consists of a single refrigeration circuit. Supply air is ducted to diffusers located throughout the classroom, and the return air uses a ceiling-mounted grill into an open ceiling plenum that returns back to the unit. The classroom has a floor area of 1,000 square feet with a 10-foot ceiling height, and the occupancy category per Standard 15 is public assembly. This system is categorized as a high probability system because a portion of the refrigerant system, the evaporator, is located in the airstream, and a leak from this evaporator would result in refrigerant being dispersed into the occupied space by the supply airstream. This is an example of connected spaces via a ducted distribution system. The effective dispersal volume is the sum of the volume of the classroom plus the total volume of the supply and return ductwork. And in this case, the volume of the open ceiling plenum since it is part of the return air path. So for this example, the total effective dispersal volume of these connected spaces is 11,500 cubic feet. Note that you cannot double dip. Since the supply ductwork passes through the ceiling plenum, its volume is already included in the ceiling plenum calculation. Starting with an A1 refrigerant, the rooftop unit consists of a single 5-ton system containing 6 pounds of R410A, so the releasable charge is 6 pounds. And Standard 34 lists the RCL for R410A as 26 pounds per 1,000 cubic feet. With our effective dispersal volume of 11,500 cubic feet, the EDVC is calculated to be 299 pounds. The releasable charge of 6 pounds is much lower than this limit, so the system complies with Section 7.3. So how about if an A2L refrigerant is being used instead? The rooftop unit still consists of a single 5-ton circuit, but now contains 5.1 pounds of R454B. Standard 34 lists this as an A2L refrigerant with an LFL of 18.5 pounds per 1,000 cubic feet. Since this is a high probability system used for human comfort, using an A2L refrigerant means that the requirements of Section 7.6 apply. The rooftop unit in our example includes a refrigerant detector to initiate air circulation in the event of a leak. Therefore, the EDVC is calculated to be 106 pounds. The releasable charge of 5.1 pounds is much lower than this limit, so the system complies with Section 7.6.1. In the second example, a VRF system conditions several private offices and conference rooms in a small commercial building. This VRF system consists of a 12-ton air source outdoor unit with a single refrigeration circuit. A ceiling-mounted cassette serves each zone. The room being analyzed is a 100 square foot private office with a 10-foot ceiling height. This system is categorized as a high probability system because the indoor cassette is mounted in the ceiling of the private office. If there was a refrigerant leak from the cassette, there is a high probability it would disperse into the occupied space. I'll start again with an A1 refrigerant. Including the interconnecting refrigerant piping, the total charge of this example VRF system is 32 pounds of R410A. The effective dispersal volume of this private office alone is 1,000 cubic feet. So, the EDVC is calculated to be 26 pounds. The releasable charge of 32 pounds is higher than this allowable limit. So the system as designed does not comply with Section 7.3.
Earlier, Chris mentioned a few ways to modify the system design in order to achieve compliance, by either reducing the releasable charge or by increasing the dispersal volume. So Chris, for this example, let's try to increase the dispersal volume.
Okay, John. For the first option, we'll increase the effective dispersal volume by connecting this non-compliant space to another space via permanent openings. As John mentioned, Standard 15 now includes equations for determining the required minimum size of these openings. This is called natural ventilation. When an A1 refrigerant is being used, here's the equation. For this private office, the net free area of these openings must be at least 0.123 square feet or 17.7 square inches. Then as long as the openings comply with the requirements of Section 7.2, which John showed earlier, this private office and the adjacent room would be considered connected spaces. This would allow the volume of the adjacent room to be added to the volume of this private office. It would increase the effective dispersal volume. Another option for increasing the effective dispersal volume is to change the equipment configuration to make use of a ducted air distribution system. For this example, instead of using a sealing cassette as shown on the left, we could change the design to on the right, which uses a ducted VRF terminal with a free return plenum. The sealing plenum can then be included in the effective dispersal volume since it is part of the return air system. The combined volume of this private office plus the entire open sealing plenum of this building is now 7,300 cubic feet, which increases the EDVC to 190 pounds. The releasable charge is now lower than this new limit, so the system complies with Section 7.3. For this example, the designer could choose either of these options, adding natural ventilation openings, a ducted VRF terminal, or some combination of the two.
Chris, earlier you also mentioned release mitigation controls. That's another option that could be used to reduce the releasable charge, right?
Yes, these are also called safety shutoff valves. And I'll actually show an example in a minute when we look at an A2L refrigerant. But as this is new technology, it's not going to be available for all products. This is especially true for equipment transitioning from A1 refrigerants. So I didn't include it in this example. So what if this same VRF system contains an A2L refrigerants? Let's assume we have a VRF system with a charge of 27 pounds of R454B. Again, this is an example of a high probability system, so Section 7.6 applies. In our example, the VRF indoor units will include a refrigerant detector to initiate air circulation. When we calculate the EDVC, it is 9.25 pounds. This releasable charge of 27 pounds is higher than this limit, so the system does not comply with Section 7.6.1. As John mentioned previously, there's a new technology called release mitigation controls. This is also known as safety shutoff valves. These valves must be listed with the equipment and the refrigerant detection system. As I stated, they may not be available for all products. In our example, the indoor VRF cassette serving the private office is now equipped with safety shutoff valves that comply with the requirements in Section 7.3. Downstream of these valves is 50 feet of copper piping to route refrigerant to and from the VRF cassette. With the shutoff valves, the releasable charge is reduced to 9.32 pounds. This is oh so close, but still higher than the EDVC of 9.25 pounds. So the system does not comply. However, most of the releasable charge in this calculation occurs downstream of the shutoff valves after they are closed. So one option would be to simply relocate the valves a little closer to the indoor unit. This reduces the charge and would allow compliance. However, for the moment, let's just leave the valves where they are. Another option we previously discussed is natural ventilation. You may notice the A2L equation is a little different. The reason is the Standard 15 committee saw a need for an additional safety factor. For this private office, if we keep the safety shutoff valves as installed in the previous example, the net free area of these openings must be at least 0.00717 square feet, or 1 square inch. All right, I know what you're thinking. This is a really small opening. And that's simply where the math worked out due to the safety shutoff valves. As long as the openings comply with the requirements in Section 7.2, this private office and the adjacent room may now be considered connected spaces, increasing the effective dispersal volume. And finally, we could change to a ducted VRF terminal. Then, the combined volume of this private office plus the entire ceiling plenum increases the EDVC to 67.5 pounds. Even without the safety shutoff valves, the releasable charge is only 27 pounds. Either way, this is lower than the new EDVC limit, and the system complies with Section 7.6.1. As I mentioned earlier, when an A2L refrigerant is used, another option is to add a mechanical ventilation system to remove excess leaked refrigerant. Since the total refrigerant charge of 27 pounds is greater than the calculated EDVC of 9.25 pounds, the quantity of excess refrigerant is 27 minus 9.25. For this example, the mechanical ventilation airflow rate required to remove this excess refrigerant is 480 CFM. And this mechanical ventilation system must comply with the requirements of Section 7.6.4, which I discussed earlier. Also, remember that the designer is not limited to one option. The designer may choose to use one of these options, like adding mechanical ventilation, or a combination of options, such as installing safety shutoff valves, changing to a ducted VRF terminal, or some combination of all the above. For the third example, we'll look at a packaged VAV system serving a small office building. The 20-ton rooftop unit is installed outside on the roof and consists of 2 independent 10-ton refrigeration circuits. Each zone is served by a VAV terminal, and the open ceiling plenum is used for the return air path. Again, the system is categorized as a high probability system because a leak from the evaporator has a high probability of entering the occupied space. The building in this example consists of offices, conference rooms, and other spaces, and this is another example of connected spaces via a ducted air distribution system. The effective dispersal volume is the sum of all spaces served by the common supplied ductwork, so long as the VAV dampers do not close below 10% of design airflow. Obviously, this is when the fan is operating. You can also add the total volume of the supply and return ductwork, and in this case, the volume of the interstitial ceiling plenum, since it's part of the return air path. Then we have the closets, the elevator shaft, the mechanical space, and the storage rooms. These are not served by the rooftop VAV system, so they are not considered in the dispersal volume. And since the vestibule and the restroom are conditioned by transfer air, we can ignore them as well. So for this example, the total effective dispersal volume of the connected spaces is just over 61,000 cubic feet. Remember, no double dipping. As the supply and return ducts are located in the plenum, we simply assume their volume is already included in the plenum volume calculation. Again, let's start with an A1 refrigerant. The rooftop unit consists of 2 10-ton independent circuits, each of which contain 12 pounds of R410A. So the releasable refrigerant charge is 12 pounds. The effective dispersal volume, the EDVC, is calculated to be 1,588 pounds. As the releasable charge of 12 pounds is so much lower than this limit, the system complies with Section 7.3.
This is pretty typical for package systems. Even if we were to change to a ducted return instead of open plenum return, the system would still comply. Now, package systems tend to serve larger floor plates, which results in a greater volume for dilution. So when using an A1 refrigerant, package systems are unlikely to exceed the EDVC.
Yeah. If we were using an A2L refrigerant instead of an A1, the rooftop unit still consists of two 10-ton circuits, each now containing 10.2 pounds of R454B. And it also includes a refrigerant detector to initiate air circulation in the event of a leak. So, per section 7.6, the EDVC is calculated to be 565 pounds. The releasable charge of 10.2 pounds is still much lower than this limit, so the system complies with section 7.6.1. For our next example, let's look at a 600-ton chiller located in a separate mechanical space inside a building. The chiller is comprised of a single refrigeration circuit containing 1,800 pounds of R134A. Standard 34 classifies this as a Group A1 refrigerant with an RCL of 13 pounds per 1,000 cubic feet. Since the entire refrigeration system is housed indoors, a refrigerant leak from a failed connection, seal, or component of the chiller would enter this enclosed room. So the effective dispersal volume is the volume of just this room, which is 32,400 cubic feet. The EDVC is then calculated to be 421 pounds. As the releasable charge of 1,800 pounds exceeds the EDVC, the space does not comply with section 7.3. In this case, standard 15 provides an alternate path in section 7.4. This is called a machinery room. John will provide an overview of machinery rooms later in this presentation. For our last example, let's look at a small chiller installed indoors. This 80-ton modular chiller consists of two independent circuits. It's being installed in a separate mechanical space and will serve a theater. The floor area of this mechanical space is 200 square feet with a 10-foot ceiling, so the room volume is 2,000 cubic feet. Again, let's start with an A1 refrigerant. Each of the chiller's independent circuits contain 32 pounds of R410A. Per section 7.3, the EDVC is calculated to be 52 pounds. In this case, the releasable charge of 32 pounds is lower than the EDVC, so the system complies with section 7.3. Note that if the releasable charge had exceeded the EDVC, then according to section 7.4, this mechanical space would have to meet all the requirements of a machinery room. However, if an A2L refrigerant is used instead, the chiller now contains 27 pounds of R454B in each circuit. The modular chiller in this example does not include a refrigerant detector to initiate air circulation, so the refrigerant charge, limit M, is read from a table in the standard. The lowest point of any opening in the equipment from which a refrigerant could leak is less than 2 feet above the floor level. So table 7-1 lists M as being equal to 4 pounds. Applying the conversion factor for R454B, the EDVC is then calculated to be 3.9 pounds. The releasable charge of 27 pounds is higher than this EDVC, so the system does not comply with section 7.6.1. So either this mechanical space would have to meet all the requirements of a machinery room, or section 7.6 allows the use of a mechanical ventilation system to remove the excess leaked refrigerant. This excess refrigerant, M sub S minus EDVC, is 23.1 pounds in this example. Interpolating from table 7-4, this requires a ventilation rate of 606 CFM. After applying the conversion factor for R454B, the ventilation rate is 625 CFM. As we do not have a detector to activate ventilation, the exhaust fan must operate continuously. As a sidebar, continuous fan operation would create an energy penalty, so it may be worthwhile to reconsider the refrigerant detector. The standard clarifies that this portion of the charge being removed by ventilation does not need to be included when determining compliance with the EDVC. Now is also a good time to mention that mechanical ventilation may also be used for addressing other indoor compressorized systems.
Another topic that comes up often is refrigerant piping. This is used to convey refrigerant from one part of a system to another. Chris, how does Standard 15 address this component of the system?
Okay, in Section 9, the standard includes several requirements related to the installation of refrigerant piping. We don't have time to address them all, so I'm going to focus on those requirements that are newer and likely important to the HVAC design professional. First, refrigerant piping cannot be installed exposed in either a fire resistance rated exit access corridor, interior exit stairway, interior exit ramp, exit passageway, or in an elevator or dumbwaiter shaft. Now, while this language sounds familiar, it is substantially different than previous edition. The previous standard used a very poorly defined term, means of egress. And this has been replaced with the term exit passageway, which is now explicitly defined in the standard. The standard also clarifies that the prohibited location is inside the corridor. As with the previous editions of the standard, when the refrigerant piping penetrates 2 or more floors, it must be enclosed in a fire resistance rated shaft enclosure. However, the standard does detail some alternatives. Rather than go into all the details, I'm going to let you review those on your own time. Something that is new is the standard requires shafts with flammable refrigerants to be ventilated. The standard gives 3 options. 2 of the options involve ventilating to an outdoor location, and the third option involves the use of mechanical ventilation. Once again, I'm going to let you read up on this on your own time. The last 2 items that I wanted to discuss involve strength and leakage testing the pipe. The standard now requires field-erected systems to be strength tested for integrity. However, components of refrigeration systems that have been listed or strength tested by the manufacturer are not required to be repeat tested on site. The obvious exception is if they've been modified or repaired. As John mentioned earlier, exempted spaces state areas of the building that only contain continuous sections of refrigerant piping or that contain only joints and connections that have been tested in accordance with Section 9.13 do not need to be considered in the calculation of effective dispersal volume. This allows the designer to avoid EDVC calculations for piping that is merely in transit. For the strength test, the system is pressurized with an inert gas for 10 minutes of the nameplate design pressure. Passing this test requires no rupture or structure failure of any system, components, or piping. After passing the strength test, the first leak test involves monitoring the system pressure for a prescribed duration as detailed in Table 9-13. For example, if the length of piping is less than 100 feet and the diameter is 3/4 inch or smaller, the duration of this pressure test must be at least 15 minutes. But for a longer or larger diameter section of pipe, the duration may be 1 hour or even 24 hours. After passing this test, a vacuum pump is drawn to 500 microns and the duration is defined in the same table. Again, the duration of the second test must be at least 1 hour, but for a longer or larger diameter pipe, it may be 8 or 24 hours. This brings us to the last item I wanted to talk about. If the system has more than 55 pounds of refrigerant, then the standard requires a contractor or engineer declaration. This is turned over to the ASHRAE certifying the system was tested and passed and is made part of the public record. As we discussed, there are more details in the application manual. I encourage you to review this at your own pace.
Before we wrap up today, John will discuss the standard-specific requirements for machinery rooms.
For larger refrigeration systems like the water chiller in Chris's example, if the refrigerant charge exceeds the EDVC limit, Section 7.4 requires that all components containing refrigerant must be located either in a machinery room or outdoors. Now, as I mentioned earlier, the term machinery room in Standard 15 is defined as a space that meets specific requirements laid out in Section 8. Now, these requirements vary somewhat based on the refrigerant safety classification. If all the systems in the room contain only non-flammable A1 or B1 refrigerants, the machinery room must comply with the requirements included in Section 8.9. If any of the systems contain a flammable A2, B2, A3, or B3 refrigerant, the room must comply with both Sections 8.9 and 8.10. And then if any of the systems contain an A2L or B2L refrigerant, with no systems containing those more flammable refrigerants, then the room must comply with some of the requirements in Section 8.9 and all the requirements in Section 8.11. Now, some requirements are the same regardless of the type of refrigerant. Most of these are self-explanatory. Tight fitting, self-closing doors, any openings to other parts of the building for pipes, conduit, or ductwork, for example, must be tightly sealed. Gasketing must be used on doors or access panels in ductwork or air handlers, and access to the room must be restricted to authorized personnel only, with clear signage posting. And then other requirements differ based on the refrigerant safety classification. For example, every machinery room requires a refrigerant detector to determine if refrigerant leak occurs, and mechanical ventilation to remove that leaked refrigerant from the room. But the specifics vary. First, you need to choose a detector that's able to measure below the occupational exposure limit, or OEL, of the refrigerant being used. This detector is used to both actuate an alarm and start the alarm rate ventilation. The alarm must use both audible and visual indicators located inside the machinery room and outside each entrance. And the sampling point must be in a location where refrigerant is likely to concentrate. Now, most commonly used refrigerants are heavier than air, so oftentimes the sampling point is positioned near the floor, below the breathing zone of the occupants. Now, if a group A2L or B2L refrigerant is used, there are some additional requirements. In this case, the standard requires 2 different alarm levels, trouble and emergency, with specific set points and response times for each. In addition, if the refrigerant concentration exceeds 25% of the lower flammability limit, the detector must also de-energize compressors, refrigerant pumps and valves, and other electrical sources of ignition. Now, moving on to the requirements for ventilation, the standard requires the use of power-driven fans to exhaust air from the machinery room in the event of a refrigerant leak. It requires 2 different airflow rates, normal and alarm. The first, normal ventilation rate, is required whenever the machinery room is occupied. This system must provide at least 0.5 CFM per square foot of machinery room floor area, or 20 CFM per person. Now, designers typically use the half CFM per square foot value because the numbers of occupants in this type of space can be difficult to predict. A secondary requirement is that sufficient ventilation must be provided to prevent the machinery room temperature from rising more than 18 degrees above the inlet air temperature, or a maximum room temperature of 122 degrees. Now, in many cases, the half CFM per square foot should more than meet this secondary requirement. But if the machinery room has a lot of heat sources like large air-cooled motors, it may be necessary to increase the normal ventilation rate to comply with this room temperature limit. The second rate is the alarm ventilation rate. This is the rate that air must be removed from the machinery room whenever the refrigerant detector indicates the concentration has risen above the stated threshold. This airflow rate is calculated based on the mass of refrigerant in the largest circuit, not the total amount of refrigerant in all systems located in the room. Now note that the equation for calculating this ventilation rate differs based on the refrigerant safety classification. To demonstrate, we looked at a 500-ton water-cooled chiller with a single refrigeration circuit. Using typical charges for the different refrigerants, you can see how the required ventilation rate varies. Fairly similar for the A1 or B1 refrigerants, but quite a bit higher for the A2L. Now next, going back to the ventilation system itself, in order to provide these two different ventilation rates, you can use either multiple exhaust fans or a multi-speed fan. Standard requires exhaust inlets to be located where the refrigeration is likely to concentrate. And the air must discharge outdoors to a location that doesn't cause a nuisance or danger. It also requires provision for makeup air to replace this air being exhausted, which must be totally separate from any other building ventilation system. And the inlets for this replacement air must be located to avoid recirculation of the exhausted air. So it's important to consider the location of the chillers and replacement air inlets when laying out the machinery room. As I mentioned, refrigerant vapor that's heavier than air will accumulate near the floor. For this reason, it's typically best to locate inlets to the exhaust ductwork below the breathing zone. And then make sure the layout provides good air movement and allows the makeup air to sweep across the refrigeration equipment before being drawn into the exhaust ductwork. Okay, let's go back to our table. If a flammable refrigerant is being used, there are additional safety requirements which don't apply to a Class 1 refrigerant. For example, the walls, floor, and ceiling of the room must be tight, non-combustible construction, and at least 1 hour fire resistive if they adjoin occupied spaces. In some cases, the room may even need to conform with special requirements of the National Electrical Code. Also, the machinery room must include remote control outside its entrance for shutting down all refrigeration equipment in case of an emergency. And finally, the standard includes requirements related to the use of open flame devices or hot surfaces inside a machinery room. Now, there's often some confusion about this last one, especially since chillers and boilers sometimes share the same mechanical space in a building. Again, the requirements vary based on the refrigerant safety classification. For a flammable refrigerant in group A2, B2, A3, or B3, the standard explicitly prohibits any flame-producing device or hot surface from being installed in the same machinery room. Then for non-flammable A1 or B1 refrigerants, the standard starts by saying no open flames, but then lists two exceptions. The first allows combustion equipment, like a boiler or furnace, to be installed in the machinery room as long as the combustion air is ducted from outside the room and sealed to prevent leaked refrigerant from entering the combustion chamber. Or if that's not possible, the second exception allows you to use the refrigerant detector to automatically shut down the combustion equipment if it ever detects a refrigerant leak. So how about the lower flammability 2L refrigerants? For this safety group, the standard refers back to the same section I just showed for Class 1, which allows either ducting in the combustion air or using the refrigerant detector to shut down the flame-producing device. So if only A1, B1, A2L, or B2L refrigerants are used, then a boiler can be located in the same machinery room with a refrigeration system, as long as it meets one of these exceptions. Now, as Jeannie mentioned, the application manual goes into more detail on each of these requirements, including the design of a machinery room.
So that's our overview of ASHRAE Standard 15. We hope you enjoyed the CNL program and that you found it a helpful way to learn about the standard. As always, the bibliography included in your handout provides more information on where to find a number of resources related to today's topic, including the application manual we mentioned. Or contact your local Trane account manager for specific information on Trane systems, equipment, controls, and services. For those of you seeking continuing education credit, check out the newest online courses at our self-paced learning portal. And fill out a survey and let us know what you thought of today's program. Finally, ask your local host for details about upcoming E&L programs. Thanks for joining us today. We look forward to seeing you next time.